whiteboard, right? Can you all see this whiteboard?
Yes.
Yes. Okay. Hearing none, I think that you can see the whiteboard. So we're going to start what we call the field of solid state chemistry. Solid state chemistry. So when we talk about the chemistry of solids, there's a lot to be done. There's a big area called solid state chemistry, which basically talks about the structure, bonding properties, and variety of other applications of solid state materials. You must have done a chapter on gases in Chem 1, and you must have done a chapter on liquids in Chem 2, but we never had a chance to talk about solids. So this is the place where we will be talking about the solid state chemistry. In other words, the chemistry of solids. Okay. Solids are extremely important from a technological perspective. Nearly all applications in computers, storage, retrieval, and also magnetic materials, electronic materials, superconductors, supercapacitors, wireless materials, dielectric materials. So think of, there are numerous amount of solids that have lots of applications in emerging technologies. So that is the reason why we need to understand the solids. All right, when we go back to the definition of a solid, remember we defined what a solid is. A solid is that part of the matter that has fixed shape and fixed volume, correct? And we also know solids, unlike liquids and gases, are most densest form of the matter. In other words, the atoms or the ions in a solid must be close packed. So there cannot be any voids between the molecules or the atoms or the ions in a solid. That's what makes the solids compact. So we're trying to understand now how do these things organize themselves. So first of all, we need to classify solids into two types. So in general, let me get another marker here. Solids are three types. Those that have an orderly arrangement of atoms, where things repeat themselves infinitely in all three dimensions, are called crystalline solids. So crystalline means they have an orderly arrangement of atoms or ions in the solid. Now the second phase is called non-crystalline. Non-crystalline are those that are solids but do not have a regular order of the atoms or ions. An example of a non-crystalline solid is glass. Glass is solid to the touch. However, there is no regular arrangement of the silicon polyhedra in glasses. Sometimes non-crystalline solids are also known as amorphous solids. Amorphous. So when you read the literature, these are all the different synonyms that you will see. Sometimes they're also called vitreous. Okay, so no matter what you call non-crystalline or amorphous or vitreous, now these solids are also extremely important in terms of applications. For example, you need conducting glasses for capturing solar energy. That's a glassy material, but it has some electrical conductivity. So, and there are also cluster gases and some magnetic materials. And there are also some non-crystalline materials used for lithium-ion batteries. So this is also a very important area, but we will not have time to work on this. We will mostly work on the crystalline solids. The final class, which are in between non-crystalline and crystalline, are basically called liquid crystals. Liquid crystals have a short range order, but they do not have a long range order that we have in crystalline materials. So they are in between liquids, which are mostly amorphous or disordered, and crystalline. So we have both the words here. So liquids, that means disorder. Crystalline means order. So there is some kind of order, but there is some kind of disorder. So these are the liquid crystals. Liquid crystals, again, are very important field of study, especially for the displays, right? You all know about LCDs. Our computers have their screens, and those materials are, again, chemicals. So in light of the fact that we don't have the entire year to work on this, we will primarily focus our attention into crystalline materials. But you should be aware that not all solids are crystalline. You can also have amorphous and liquid crystals. The next thing is, even within the crystalline materials, we have three different types. So crystalline materials can be subclassified into three types. Ionic crystals. A classic example of this is going to be sodium chloride. Sodium chloride is an ionic crystal. Similarly, calcium oxide, calcium carbonates, and most of your ceramic materials, they're all ionic solids. You also have covalent solids, where the bonding in the crystal is primarily covalent. Like, for example, if you look at graphite or diamond, so the bonding between two atoms of carbon in diamond is mostly covalent. There are no ions involved in this, right? Same thing happens in the graphite. So these are all covalent solids. Most of the organic solids fall into this category. Sometimes they're also known as molecular solids. So if you look at pharmaceutical compounds, right, like esomeprazole, or if you're looking at ibuprofen, or if you look at any of these anti-cancer drugs, they're all solids, but those solids are molecular solids. They do not have extended three-dimensional network connectivity. Watch my words carefully. So that's what we mean by saying molecular or covalent crystals. Finally, we also have what we call metallic crystals. Metallic crystals are basically, if you look at copper metal, silver metal, okay? So these are not really atoms nor ions, they are somewhere in between. So we have bonding, what we call a metallic bonding, between the atoms of the metal, such as copper or silver or gold, whatever you may have. Most of the metals in the periodic table are conducting. So the conducting metals, again, have metallic bonding, where what happens is there is a bond between the atoms, but the atoms also lose their electrons to form a sea of electrons on the top that does all the conductivity of the metal. So these are the three different types of solids. So because of time limitations and the amount of work that we need to do, we'll mostly be concentrating on ionic solids, some on covalent solids, and some on metallic solids. But we will put more emphasis on ionic compounds because there are plenty of ionic compounds in the literature, and we need to understand the structures, the connectivity, and all that stuff. Okay. Now, the million-dollar question is, how do we know what is the arrangement of atoms in any solid? For example, if you look at salt and sugar, right? Salt is an ionic compound. Sugar, on the other hand, is a molecular solid or a covalent solid. The issue is they look alike. You will not be able to distinguish the salt from sugar, especially if it is powdered well. Similarly, diamond is different. Ruby is different. Emeralds are different. Graphite is different. So it's not that humans did not know the existence of solids, but how do they examine and classify? That curiosity of the humans started a long time ago, almost from the time of diamonds. When the humans came across diamonds, some of the hardest materials known to humans. As you know, right, diamond is one of the hardest materials, and it has a very good optical reflectivity. And for that reason, it is used extensively in jewelry applications, and similarly, emeralds. So now, the question then is, how did the early humans find out the identity of a diamond, for example? For example, sometimes you can go to a jewelry store and you may buy what we call artificial diamonds. Artificial diamonds, they look exactly like diamonds. So for a naked eye, for an untrained eye, you will not be able to know the difference between them. So what is the best way to really then study the crystals, especially if we did not have all the sophisticated instrumentation? Right? So early humans used all the crystals have faces, right? So a face like this and another face, and then a face, and then a face. So most crystals have faces. So what people used to do is they used to measure the angle between the faces, and that angle is almost like a fingerprint of a solid. So the interfacial angles of a crystalline material serve as an indication of the identity of the crystal. So in the early development of the solid state chemistry, especially when people had no idea about chemicals, periodic table, or the sophisticated techniques such as X-ray diffraction that we have today, people used to look at the angles between them. So even a powdery material, even if it is a polycrystalline material, it is composed of extremely tiny crystals. So for example, if you take sodium chloride, rock salt, and if you start grinding it, you are reducing the size of the crystals, but you are not breaking the crystal structure though. So sodium chloride, for example, when you powder it, we get a polycrystalline salt. So if you now use a magnifying glass or a magnification technique such as scanning electron microscope or electron microscopy, when you look at the structures, you will see very clearly even the tiny particles are crystals with well-defined faces and interfacial angles. So this is the story, but today we do have a much better understanding of how the solids assemble themselves, how do they form, and how do we manipulate the chemical and physical properties of the materials. So with that small introduction, then we'll move on to the fact that, as we all agreed in the beginning, that the solids are extremely dense form of the matter compared to either liquids or gases. So it's quite likely that these atoms or ions should be packed very close to each other. So if you look at that arrangement there, there are no spaces. So when you draw the second layer, for you to be extremely space efficient, you try to use the gaps between the circles in the first layer. It's almost very similar to the way you pack oranges in a crate. So you put the first layer, and the second layer is not exactly on top of it, but we use the space in between the spheres to load them, and the third one will go like this. This is the two-dimensional arrangement. This arrangement, for a trained eye, when you look at this particular circle here, or this particular atom, it is surrounded by 6 others, right? So this is almost like a hexagonal packing, like a benzene ring. Right? And then when you develop the third layer, so this is in the two-dimensional space, when you put an additional atom, again, you put that additional atom in the gaps located from the 3 spheres below. So it's like packing the oranges. You pack the first layer, then you go to the second layer, and third layer, and fourth layer, so on and so forth. So there is an order here that we use. So if you look at the top sphere and the bottom 3 spheres, and if you focus your attention only on that one alone, it looks like a tetrahedron. 1 on the top, 3 on the bottom. So if you look at 3 on the bottom, 1 on the top. So that's your second layer atom. And these 3 atoms are in the same layer. Okay. So again, there is a small space in between the top atom and the bottom 3 atoms. That small space is what we call a tetrahedral hole. Tetrahedral hole. Sometimes we also call the T-hole. Okay. So you can start now packing up these things. And here again, when you start packing, you will see again a small space in which you have 1, 2, 3, 1, 2, 3, total of 6 of them with a small space. So that hole is called an octahedral hole. So O hole. So most solids have only 2 types of spaces in between them. One is a tetrahedral hole, one is an octahedral hole. So the entire solid state chemistry now, to a large extent, depends on the occupancy of octahedral and tetrahedral holes. We will get into that more detail as we get into different arrangements. Are there any questions up to this point? Okay. So now let's look at some of the arrangements these atoms can have. Let's say I have 2 atoms So 1, 1, 1, 1, these atoms are in the bottom, and the 2, 2, 2, 2 are exactly on top of 1, 1, 1, 1. All right, in this space, if you have such an arrangement, then you can perhaps draw lines between all the 1s and between all the 2s and join the lines here. These are all imaginary lines. Okay, so the resulting pattern looks like a cube. Again, it's very important to note that these lines are only for the convenience of eye. They don't exist in nature. In nature, all solids exist like atoms or ions. There are no lines. It's only for human visualization, for our convenience, we look at these lines here. Now, so this cube is one example. A cube, as you know, is a member of what we call parallelepiped family. You heard of the parallelepipeds, right, in mathematics? An object that has straight edges and angles between them. The reason why we use parallelepipeds is because only parallelepipeds will allow us to achieve what we call packing with no gaps. That is the reason why we use the parallelepipeds. All right. Before we continue our discussion with the parallelepipeds, it's also important to know what type of geometries are generally seen in nature. To understand that, we will get back to day-to-day life example. Let's say if you want to buy some tiles to fill the space in your bathroom floor, right? Just for the sake of argument, what type of tile shapes that you use? Can I use square tiles? The idea is when you put these tiles on the floor, there should be no space left between them. Okay, that's the key point that you have to keep in mind. You can also have triangular tiles. You can also have hexagonal tiles. You must have seen that in nature, right? The tiles are generally usually squares or hexagons or triangles. What you will never see in a tile is what we call a pentagon. Have you ever seen a bathroom floor? Can you use a pentagon-shaped tiles to fill the space without any gaps? Clearly not, right? There's no way you can do this. So what exactly is going on here then? We all know about the symmetries, right? If I have a square, what is the highest fold rotational axis of a square? The C3, C2, C4, C5, C6, what is it? One of you can perhaps open your microphone and then answer.
C4?
You're absolutely correct, sir. That is a C4. How about triangle? How many degrees you need to rotate this triangle before you see a similar looking shape? The 60, 120, 180, what is it? One of you can open the microphones and talk. Just want to make sure. Otherwise, if you want to believe whatever I say, then I will not ask you any questions. Just follow my instructions.
Wait, you're turning the triangle?
Yeah, triangle.
But it can't make another shape. It's always going to be a triangle.
Yeah, but how many degrees I have to rotate this triangle before I can have this similar looking triangle?
120?
That is 120 because if you draw those lines, right, that angle is 120. So 360 divided by 120 is 3. So we say there is a C3 axis of symmetry for the triangle, highest fold rotation axis of symmetry. What is it for the hexagon? So again, if you draw the lines here, right, that angle is 60 degrees, correct? So as long as you rotate this object 60 degrees in a direction that is perpendicular to this plane of the hexagon, you get an object that looks exactly like the hexagon before. No difference. So we say this is a C6 axis of symmetry here. Similarly, for the pentagon, we have C5. Sometimes you can also have an object that will have only C2. That's also fine in terms of filling the squares or filling the space on the floor. So the only thing that is not useful for space filling, I'm sure you're watching my words carefully, I'm using the word space filling the space, is the C5. And quite surprisingly, all solids use either C4, C2, C6, C3, but you will never find a solid that has a local symmetry of C5. In a molecule, it might exist, but in a solid, it will not. That is where the shapes of molecules and shapes of solids differ. In a molecule, you can have a C5 symmetry, but when you are doing an extended network of solids, you will never see a C5 because C5 is not an efficient space-filling geometry. That is the key word that we need to understand. So we'll never see C5 symmetry in solids. That is the source. So I just gave you the reason. If you don't like the reasons, if you want to memorize, that's fine with me. Just say that C5 never occurs in solids. Wonderful. So now that we know this, next thing is we need to talk a little bit about what we call the parallelepipeds. Again, when you're drawing these lines, it's also very important because these lines do not exist in reality. These lines are only for our convenience. And it is also very important to make sure that you draw the lines properly. I'll give you an example of how to draw this. Let's say I have a line of atoms this way. 1, 2, 3, 4, 5. 2, 3, 4, 5. There are 3 rows of atoms. Okay. I can draw a line this way. That's one. Or I can also draw a line like this. Because, that's my choice, right? So if you are given with multiple choice of connecting the dots, which ones should you take? Tricky question, right? Yeah. Why can't I draw a line like this where the atoms stay on the middle of the edge here? In here, I have the atoms staying in the corners of the square. So which one is more applicable or more agreed upon or approved? The key factor here is whenever you draw the lines, you draw the lines in such a way that the highest symmetry elements are present. So if you look at a square here, if I have 4 atoms, there is a C4 axis of symmetry. If I draw a line like this with only 2 atoms, this will drop to a C2 symmetry. C4 is a higher symmetric order compared to C2. So we should always join the lines or the dots in a way that we get highly symmetric, the most symmetric configuration that you can draw, not the least one. So this is how we draw the lines. So once you draw the line, you can have a parallelepiped. For those of you who need a refresher, just let me give you an idea about what a parallelepiped is. It looks like this, where you have the origin here. It has a length A, B, and C. These are the lengths of the parallelepiped in 3 different directions, X, Y, and Z. And then you have the angles between A and B, A and C, and B and C. So the B and C is called the alpha, and the angle between A and B is called the gamma, and the angle between A and C is called the beta. So in a parallelepiped, you can have different A's, different B's, different C's, different alphas, betas, and gammas. So depending on those values, we will have a maximum of 7 crystallographic systems. So you can have a situation where A equals B equals C, all the sides are equal, and all the internal angles are 90 degrees. What do you think this geometry should be called? If all the internal angles are 90 degrees, if all the sides are equal, we have a name for the geometry. What do we call? I wonder how many of you are still on the talk here.
Symmetric?
Symmetric, but we have a geometric name for this, right? Something that has...
Octahedral?
No. We have a name, folks. Say, for example, I have a cube like this, right? Can you all see? I think I gave you the answer already. All sides are equal. All the internal angles are 90 degrees. This is what we call a perfect cube, right? That's the name that we use. to describe this. So such systems are called cubic. You can also have a situation where A equals to B, but not equal to C, but all the internal angles are 90 degrees. So what do we call this now?
Would it be just a rectangle?
Yeah, it's like a rectangle. So this is a shape like that looks like this. So it is elongated along this direction, but if you look at the base, it's exactly the same. So on the floor, the sides are equal, but on the vertical, the length is higher. That is an example of A equals to B not equal to C, but all internal angles are 90 degrees. This is what we call a tetragonal. Tetragonal is the geometry. If they are all equal internally and sides, that's called cubic. But if one side is longer or shorter, but if the two other sides are equal, and if all the internal angles are 90 degrees, that is classified as tetragonal. So you can also have situations where A equals to B equals to C, but let's say A not equal to B, not equal to C, but all the internal angles are equal to 90 degrees. You can have a situation where the sides are unequal in all sides, but all internal angles are 90 degrees, which is what we call orthorhombic. Okay. Just to give you an idea, most of the pharmaceutical compounds, organic molecules, they adopt orthorhombic symmetry in general. Well, there are exceptions for everything, but if you look at any drug molecule like aspirin or ibuprofen or any of those pharmaceutical ingredients, if they are crystalline, in general, they tend to be orthorhombic. Similarly, you can also have a system where A not equal to B, not equal to C, and alpha and beta are 90 degrees, but the gamma is not 90 degrees. So the sides are not equal. This time only two angles are 90, but the third one is not 90. That one is what we call monoclinic. This is also seen, especially most of the outer space materials. They tend to have monoclinic symmetry, slightly distorted orthorhombic, you can say. And you can also have a system where A not equal to B, not equal to C, and alpha not equal to beta, not equal to gamma. So all sides are different lengths, all internal angles are very different. So when you have a situation like that, this is called triclinic. So from going from cube to tetragonal to orthogonal to monoclinic, the symmetry is definitely changing. Cube is the most symmetric form of solid, but once you start going down, the number of symmetry elements start reducing. So we have two other systems. We can have A equals B equals C, and alpha equals beta equals gamma. The only difference is that they are not 90. So you can have the situation where all the sides are equal, all internal angles are equal, except they are not 90 degrees. So if you look at the geometry that I'm holding in my hand, that shows that. So all the sides are exactly equal, but the internal angles that we are talking about between A, B, and C, they are different. So that is what we call a rhombohedra. So the difference between cube and rhombohedra is that they have very similar geometries. Sides are equal, all the internal angles are equal, except the differences in cube. All internal angles must be equal to 90, but you don't have that condition in rhombohedra. That's the only difference between a cube and rhombohedral. Okay? There are several solids that also adopt this rhombohedral geometry. Finally, you can have a system where A equals to B but not equal to C. Alpha and beta are 90 degrees and gamma is exactly 120 degrees. That is another parallelepiped with those conditions. And when you have that, that is called hexagonal. So how many we have now? We have 7 crystallographic systems here. We can have a cube, tetrahedra, orthorhombic, monoclinic, triclinic, rhombohedral, hexagonal. The beauty of it is, although there are millions of solids that are available in the nature, all solids, crystalline solids, must belong to one of the 7 systems. There's no way around it. When you are having a closed packed system, all crystalline solids must belong to one of the 7 systems. You cannot have anything more. Even if you leave this planet, go to Mars, go to Jupiter, go to Moon, get solids from there, get the rock samples, sand samples, do the analysis, they must belong to one of them. This is mathematically sound geometrical representation of the solids. Isn't it wonderful that although you may have millions of solids, they must belong to one of these simple 7 crystallographic systems? Questions up to this point? As we are moving quickly on this, we will not have time to come back and do all these things. So it's very important to get any doubts that you may have right now. Of course, you can also read the PowerPoints that I sent you and get some information, read the book chapters to get an introduction. But I'm trying to summarize here in a simple terms. The next thing is, even between the 7 crystallographic systems that we have, that is cubes, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral, you still have different possibilities between the cells. So let's start with the possibilities here. This is a simple cube. If you have atoms or the bases only at the corners, but nowhere else, then we call this primitive cubing. The primitive cube cells are given a letter P. So when they say P-type cube, basically what they're telling you is this is cubic with atoms or bases. Now I'm using a strange word here. We call these points here lattice points. Sometimes in a crystal structure, you may have atoms exactly at the lattice point. Or sometimes you may have a solid in which, let's say, if I have a disulfide. Now, the middle of the sulfur-sulfur bond point can be at the lattice point. So you don't have to have always atoms. You can also have what we call basis points. Or sometimes it could be octahedra, where the center of the octahedra is located and all the other atoms are around it. Okay? So this is what we call the primitive. In addition to primitive, the primitive cells are possible in all 7 crystallographic systems we said. That is cubes, tetragonal, orthorhombic, monoclinic, triclinic, rhombohedral, hexagonal. All 7 systems can have primitive. In addition to primitive, we can also have another cell where, in addition to having lattice points at the corners, we also have a lattice point located in the center of the cube. This representation is called body-centered cube. Sometimes it's known as BCC. Again, as with the primitive cells, the lattice points may coincide with the presence of an atom, or it could be a basis. Okay, good. So this is this body centering is possible only in 3 types of the cells we talked about. So those 3 are cubic, orthorhombic, and tetragonal. So if you have a cube or an orthorhomb or a tetrahedra, you can have the body centering, but you will not have body centering in rhombohedral, hexagonal, or monoclinic or triclinic. So those cells cannot have a body centering. The only 3 systems that can have body centering are cube, orthorhombic, and tetragonal. In addition, we can also have another type of cell, which we call we have lattice points at all the corners, and we have lattice points on the centers of each face. Remember, cubes have 6 faces, and if you place an additional lattice point at each of the faces, then we get what we call face-centered cube. That is called FCC. An example of an FCC is right with here, if you can see, all of you. This is a cube, and if you look at all the faces, there is 1 atom in the middle of all of them. That is a classic example of a face-centered cube. In a body-centered cube, you have only atoms at the corners and 1 in the middle. It is very important to know that you cannot have a different atom in the middle compared to what you have in the corners. They all must be identical. If they are identical, we call that BCC, or body-centered cube. If they are different, we say it is BCC-like, not exactly BCC, not body-centered cubes. Am I making sense here, folks? That is the 3rd one. The 4th variety, let me also give you some names for this. The body-centered cubes are given the letter I. The face-centered cubes are given the letter F. Finally, you can also have a very strange system in which you have atoms at the corners as well as only in the opposite faces. It could be along A, B, or C, but only in one direction you have this. These are called side-centered cells. So a side-centered cell will have atoms only in the top or the bottom, but not on the other side. So let me give you an example of a side-centered cell. If you look at this is a monoclinic cell, and it has side centering. So these are the atoms, if you can see my finger here, those two atoms are on the opposite sides, and then you have atoms at the corners. So that is a classic example of a site-centered monoclinic cell. So the site-centered cells are generally called as A, B, or C, depending on which faces they have the atoms. If they have it along the A, then we call it A type. If they're on the B side, B type, it's B type, and C type. All right, so this is the site centering. So the face centering is possible only for cubes and orthorhombic materials or the crystal systems. And the site centering is possible only in the orthorhombic and monoclinic. Okay, so let's see what we have now then. We have 7 primitive systems, plus we have 3 body-centered types and 2 face-centered, and we have 2 site-centered. So when you add all of them, 7 plus 3 plus 2 plus 2, 14. This is the magic number. So collectively, these 14 lattice types are called Bravais lattices, B-R-A-V-I-S, that S is silent, Bravais lattices. Am I making sense here? So any crystal system that you encounter in the entire nature, again, must belong to one of those 14 Bravais lattices. So the point here is we have primitive cells, we have body-centered cells, 3 of them, face-centered, 2 of them, and side-centered, 2 of them. Makes a total of 14 Bravais lattices. And any solid, whether you talk about sodium chloride, whether you talk about sugar, whether you talk about quartz, emerald, rubies, all kinds of crystals you can ever think of, they must all belong to one of those 14 Bravais lattices. Am I clear here, folks? Questions? It's good. Let's now move on. If I don't hear any question, there are 2 possibilities. Either you understand everything or you understand nothing. One scenario is wonderful, the other one is scary. The next thing that we need to work on is what we call the effective number of atoms. Let's talk about a face-centered cubic system where you have atoms in the corners and atoms at the center of each face. There are 6 faces, so there are 6. So how many lattice points do you see now in this cube in isolation? You have 8 corners and 6 face-centered positions. So you have a total of 14 atoms. However, we have to keep in mind that this is the smallest part of the unit cell. In reality, solids have another face-centered cell next to it, another one next to it. So this is a small brick through which this entire structure is built. So by understanding this brick, we can understand the structure, but we have to keep in mind that these cubes are not in isolation, they're all connected. So it's imagine that you are in a multi-story building, you're living in a cubical cell where you have another cube on top of you, one cube below you, one cube on the side, everywhere surrounded, okay? Now, if that is the case, let's now look at the points at the corner. How many cubes share this corner? when you have a cube above this, on the side, this way, that way? So imagine you are sitting in a cubicle, right, where there are cubes above you, below you, on the side. If you drill a hole in the corner, how many rooms can you see? Basically, we're trying to see to how many cubes this corner atom is common to. So if you're sitting in a room, you can imagine, right? You put a camera in the corner and imagine that you have, you're surrounded by the same type of rooms that you're sitting in right now. And if you draw a corner hole, how many rooms can you see? 2, 3, 4, 5, 6, 7, 8.
8?
You are absolutely correct, sir. There are 8 of them. So each atom in the face-centered cube in the corners contributes 1/8. Similarly, what about the face-centered point here? How many rooms this is common to? If you drill a hole on the ceiling, top ceiling, right? How many rooms can you see?
Would it just be 2?
2. You are absolutely correct. So this one contributes 1/2. If you have an atom in the center of a face, it contributes to 1/2. What if you have an atom in the middle? Is it shared by any other cube? Obviously not, right? You're locating the lattice point in the middle of the room. That lattice point belongs to that room, so its contribution is going to be 1. Similarly, if I have a lattice point on the center of the edge here, how many cubes share this point?
Is it 4?
You're 4, absolutely correct, sir. That is 1, 4. So it's important to note the position of the lattice point in a given crystal lattice and its contribution to the unit cell. So now that we know this, let's go back to, please keep a note, write down this. Of course, you're going to have this video too. But let's now try to count the effective number of atoms then in a face-centered cubic. So I'm going to draw the face-centered cube again one more time. This time I'm going to put crosses at all the lattice points. They're all identical. For a visual purpose, I'm going to show this to you. This is the 3-dimensional picture of that drawing that I'm putting there. That is your face-centered cube. You can see the lattice points at the corners and lattice points at all the centers. Okay. All right, so we just recognized that the corners contribute 1/8 and the centers contribute 1/4, 1/2. So we have 8 corners, right? So the total contribution of atoms at the corners, each corner contributing 1/8, and 8 times 1/8 will be the contribution from the corners. And I have 6 face-centered positions, each contributing 1/2. So what is that total now? 8 times 1/8 plus 6 times 1/2 is 4. So for a face-centered cube, we say the effective number, just like the effective nuclear charge, in solids, the Z is different. The effective number is 4 for a face-centered cube. Am I making sense? Okay, so if you take this cube, separate it out from this solid and put it in the balance, you will find the weight of this cube is 4 times the weight of the atom inside this. Not, although there are 14 atoms you count, not all atoms contribute to this because some of the atoms are shared by the other cubes. So the effective number of atoms in this case is going to be 4. Similarly, if I have a body center cube, so just to give you an idea of the body center cube, right now I have atoms at the corners and one in the middle. Okay, that is the body center cube right here. So what will be the effective number of atoms body center cube will have? To do that again, I have 8 corners, 8 times 1/8, plus I have 1 in the middle that's not shared by other cubes, so that makes it 2. So for a BCC, it is 2. For an FCC, it is 4. Okay. If I have a primitive, for a primitive cells, there are only corners, 8 corners, 8 times 1/8 is 1. What if I have a site-centered cell? In a site-centered cell, again, I have 8 times 1/8 corners, plus there are only 2 atoms on the centers of the faces, so that makes it 2. So site-centered gives you 2. So if you have a site-centered cube like this, the effective number of atoms this cube has, just 2, only 2 atoms weight. Am I making sense here?
Dr. Char, I have a question. Does that mean that the cube with the packing where the Z was 4, does that mean that's the best way to pack them? Like
Correct.
you get the most weight in it?
Right, right. I will show you as we go through these lectures, this is the best possible way you can pack. You will never get 100% efficiency in packing. I'll just ask you to think about this. Can you pack oranges in a 3-dimensional space with absolutely no gaps? Can you do that? If you can't do that with atoms, if you can't do it with oranges, you can't do that with atoms either. There is bound to be a small space, but we're trying to minimize that space. That's what we're trying to do. So the pictures that I have shown you, right, in a body-centered cube, this is not really efficient, but this is efficient compared to primitive. Face-centered cube, on the other hand, is the most efficient packing. You get about 74% packing efficiency. That's about it. In a body-centered cube, you get about 68% efficiency. In a simple cube, it's going to be 52%. Okay. Despite all that, there is one element in the periodic table that crystallizes with a primitive cubic structure. Anyone knows what that element is? It's a strange one. We still don't know why that fellow adapts a primitive cubic structure, despite the fact that is the most inefficient way of packing. Nature somehow was not careful with this element, and that element is polonium. Polonium is the only element in the periodic table that crystallizes with a simple cubic structure. That's a simple primitive cubic. Questions up to this point? Anything that is not clear? Let me ask you some things here. Let's say, let's play a game here. let's have a solid with rhenium metal in the middle and oxygens on the centers of the faces. What should be the formula of this oxide? So how many effective number of rhenium atoms you have in the structure? This looks like a body-centered position, right? So can I say that effectively there's only one rhenium? How many oxygens you count here? We have 6 of them, but unfortunately, they are shared by 2 other cubes, right? So you have 6 oxygens and their contribution only 1/2. So the formula of this then should be ReO3. In fact, in reality, rhenium trioxide crystallizes, that solid has exactly the same crystal structure. Let's do one more. So when somebody gives you a crystal structure, you should be able to know what the formula of the compound is just by using the simple principles. So let's imagine I have titanium in the middle, oxygens on the centers of the faces, and barium on the corners. What should be the formula of the solid? Formula means the simplest ratio of atoms in their formula. If you have bariums at the corners, how many effective number of barium atoms you have here? You have 8 corners, right?
Would it be TiO3Ba?
That is absolutely correct, sir. So we go by barium. The reason why we write this way is we look at the most electropositive metal on the left and most electronegative element on the right. That's how we write the chemical formulas, right? When you write sodium chloride, you write sodium first and chlorine next, correct? You will never write sodium chloride as ClNa. Similarly, we go by the most electropositive metal, that is barium. So there are 8 of them. Because they are in the corner, their overall contribution to the cell is only 1 atom. Titanium is in the body center position, so that is going to be in the middle. And I have 6 oxygens, but they only contribute 1/2. So for barium, it is 8 times 1/8. For titanium is 1 times 1, and oxygen is 6 times half. So the formula of this is BaTiO3. This is one of the very high dielectric materials. So this is the structure of that compound BaTiO3. And one of the very earlier applications of this material was on the, you all remember the vinyl plates where the music used to be stored? You must have seen in your grandparents' homes, right? The vinyl plate disc that rotates, and then you have a needle on top of it, right? As the disc rotates or the needle, you get the music played. And if you are trying to understand what the hell happens, folks, this is this compound that does the trick. So when you take this compound, when you put a needle on this crystal here and you run through the grooves, and vinyl plates have grooves that have what I call micro hills and valleys, small hills and valleys. So it kind of bumps up and down. So this needle, when it hits this crystal, it develops a charge. That's what we call piezoelectricity, pressure-induced electrical polarization. That's what happens on this material. And that potential difference can be now amplified to give you the actual sound. Isn't it wonderful? That inorganic compounds have been part of our day-to-day lives. Although many people may not recognize, people who use this, but as chemists, we are very curious, like what the structures are, and this is the compound, that's the application, and then I show you the structure, and I tell you how to write the formula. Am I making sense here, folks? Let's put one more. Here's the structure of a real compound. I have silicon atoms located in a body-centered fashion. That is, on the corners of the cube as well as in the middle. And I have vanadium atom as pairs, two vanadium atoms, like a diatomic pair, sitting on each of the faces. What should be the formula of this compound? So you need to find out how many effective number of vanadiums are, how many effective number of silicons are, and take the ratio. That's all it is. So how many effective number of silicon atoms do you have in this, in a body-centered position? Remember, we said all body-centered position, the effective number is 2. So we have 2 silicons. Each vanadium pair is, like you have 2 of the cubes. So only 1 vanadium belongs to this. So we have a total of 6 vanadiums now. So if you count, there are 12 vanadiums, but since they contribute 1/2, because they're situated in the center of the face, that makes it 6 vanadiums. So the ratio of vanadium to silicon is Vi6, or sometimes it's called that V3Si. This is sometimes known as the beta tungsten structure. And is seen in many compounds that exhibit superconductivity. Okay. So anyway, that's 3:15 now. So we will continue next Tuesday on some of those calculations, packing efficiencies, density calculations based on the crystal structures, Miller indices, and then we will talk about diffraction techniques and some applications of perovskites, and then Born-Haber theory, Kapuscinski's equation. So we should be able to finish that by next week. Okay. Some of the slides that I have posted on the